12, the vectors, maybe until 12.4, reviewing until the cross product, and maybe we will try to relearn the vectors that we already know. And next week, I'm still continue on vector until finish. And after that, we will go to some review for chapter 10 and chapter 11. Because I believe, especially in chapter 11, we need to have more review and more exercises, because the important things in chapter 11 is to trial and error. Because there are a lot of methods, and if we do not have many exercise, you will get sometimes maybe mixed up with all the things inside the chapter 11. Okay, so today chapter 12. Next week, Tuesday, still chapter 12. And Thursday next week, still a little bit of chapter 12, and maybe finish the chapter 12, and we can go to review our chapter 10 and 11. Okay, and after that, 2 weeks after that, still we can still review before we have midterm, and then we will have midterm. Okay, so I will have 2 days for reviewing chapter 10 and 11. Okay, I hope we will have enough time for preparations, and you can get to know more about what we are learning in chapter 11 and at chapter 10. Okay. Now we are continue our study on vector. So we are in the length now. How to find the magnitude or the length. Usually you will see this the symbols. You can use the symbols as this, like this, or this is also fine. Both are commonly used in physics also and mathematics. This means the term is the magnitude or the length. Okay. So vectors is actually quite abstract concept. Okay, so it can be anything as long as you can define the value and the direction. So that's the vector. And to apply those vectors, usually we can imagine the physics, the phenomenon in physics, okay? Like force, magnetic fields, electricity, and so on and so forth. Okay, so something that has value and direction. Okay, and sometimes you cannot see it with your eye, so that's why we need approach from physics. Okay, now let's continue. After we get the length, the other thing is if we can, how do we add the or subtract the factors? So basically, I'm just reviewing the introduction part of vector. So if you maybe remember, or maybe you need to refresh, okay, I will show you how and maybe some examples. So you can add, for example, the factors as adding each axis. Or you can minus them, just subtract them. Or you can multiply with a scalar. Let's say this is scalar. So you can multiply with scalar, and you'll get CA1 and CA2. And the same for tridimensional. So this is for two dimensions. The 3 dimension is also the same. Okay, This is very basic. I think you already know. And the other things is maybe the some property of vectors. Okay, and I think this is also not too complicated because it's you already done in some calculations, I think. So if let's say, so if A, B, C, all is vectors. Vectors usually we are using in Vn. Vn is a space, okay? And let's say D, E is a scalar. And someone, can you help me? Can you help me? The microphone is, the battery is empty. So I need to. Okay, okay. Okay, while we are waiting, let me write this property. Okay. Now notice the difference. I put, uh, I'm using ABC is the vectors and DE is the scalars. In your textbook, they are using the same C. So to avoid misconception, I'm putting D instead of C. So D or scalar. So, and I think this is well known. So I think intuitively in math, it's also similar. But the difference is in every vectors, you will have a component of x, y, or x, y, z. Okay. Okay, this is the property of vectors. Um, the other important thing is the standard basis vectors. Usually, you are familiar with the um, I, J, and K, right? That's called the standard basis vectors. Standard basis vectors. Why we need I, J, and K? Let me write the graph first. Okay. So this is what looks like. So this is I, J, and K. So what does that mean? So I, J, and K each of the vectors having one unit length. Wait. Someone trying to screen mirror my laptop. So wait, I think you didn't realize what's happened. Okay, wait. Okay, I'm closing his windows. I hope he don't realize that. Okay, now ijk is let me remind you again. It's a vector with one unit length. Its direction is each of them is positive x, positive y, positive z. Okay, so we need ijk to rewrite our equation, okay, in the vector. So we can have, like, for example, 4i minus 2j plus k. So let this be our vector. So this is, we can also write in 4 minus 2 and 1. Okay. Okay, this is just a reminder how to write a vector. Okay. Okay, that's called the standard basis vectors. I'm still don't know why we are using the terms I, J, K. Anybody know? Did you know? I think I heard somewhere, but I forgot why. Do you know why? Why we write the I, J, and K? Well, in terms of alphabets, it's I, J, K, right? But why we are using that? But maybe later for other discussion. But not really that important in calculus. Okay, and then after the I, J, K, we also have the terms called unit vector. The definition is a vector whose length is 1. So if the, let's say the vector A is not 0, well, let me write A is a vector. If vector A is not 0 or non-zero vector, then unit vector, well, let's say this is unit vector, is 1 divided by the magnitude of A and multiply with A itself. So, or we can just write A divided by the magnitude of A. For confirm this, we can prove or just let using some, that C is equal 1 over magnitude of A, and then our U is CA. So C is a scalar, right? Because it's only magnitude of A. And because of that, the U and A both has the same directions. So if we calculate the magnitude of U, this is the, we can write like this. And it turns out that it is confirming that it's actually 1, the length. Okay? Just a simple confirmation. Okay, that's the unit vector. There is some example and application, but I think it's more likely in physics. But as long as you understand how to evaluate the vectors in calculations, I think you shouldn't be any worry about that. Okay. Okay, now the next thing after the unit vector, we go to the next sections. I think we can move to the next page. Or do you have any questions here? Okay. So actually, the vector, the concept itself is, I think, already old. It's maybe 1700, I think, or the cross product is 1800, so it's already a long time ago, which is, I think, quite interesting because it's already a long time and we're still learning that that thing, right? So the next concept is the dot product. So dot product, literally, why we need the dot product? Okay, so if A, B is vectors, and C, let's say it's scalar, we already know how to add the vectors, right? We can add let's say we add, and maybe we multiply with scalar. We know that, right? CA1, CA. But how about if we multiply factors? Okay, that's the questions arise why we need the method or dot product. So when the product of this results, okay, from this result, this is a scalar result. And the definitions, let me just write definition first. So definition. If you have a vector, two vectors, A and B, then the dot product of A and B is number A dot B given by okay. So the results is a scalar product, or sometimes it's called inner product. Okay, this is just a definitions official, like the dot product of A and B is number A dot B given by. So meaning if we see A dot B, like these terms, this is the dot product of A and B. Just like official terms or official definitions. But I believe you are already familiar with the calculation itself. And we have the properties for dot product. So if you are dot the same factors, you will get the magnitude and square. And you can reverse the sequence, same thing, because you are multiply and add, and that's the scalar, the result. And you can also dot the additional factors, and you can expand this into two dot product. And if you have a scalar, let's say D, let me write this as a scalar, and A, B, C is vector. And you can exchange all the scalar that you find in the dot product. That will be the same. And if you are multiplying with 0, then all the calculation will be 0. I think this intuitively already in, I think, in your calculation in your mind, right? And I think not really, you don't really need some proof for this. Okay? But I think for the next one, I think you need. And how do we observe the factors? We can observe the factors through some graphs or some pictures. So let me draw. Let's say this is A. We start from origin. This is point A. And then we also have the other factors. Let's say that's our factor. Let's say this is B, vector B. Okay, let's say we have, or we want to observe what is the product from A dot B. Okay, so from vector A and then vector B, we multiply both of them. So to observe these situations, we can apply some angle between these two vectors. So let's write some notes for the angle. So let the theta angle between A and B. Or OA segments and OB segments, in which the angle theta is between, or let me write in terms of like this. So the angle theta can be from 0 to pi. So if A and B parallel, then theta is 0 or theta is pi, right? Meaning it has the same same lining here. Okay, that's some notes. Now let me write the relations in between all of this, and later I will give you some calculation to prove. So from here, actually we can write. Let me just write first and then explain later. We can also write the dot product as these relations. A dot B equal magnitude of A, magnitude of B, and cosine theta. Okay. Why cosine? Let me explain later. To understand this dot relations, we go to our triangle here. Let me draw one line here to make it a triangle. Okay, let's say it's the factor A minus B. Okay. So this is A. B is here. Okay, let me move B here to become negative. So we have this factor, right? A minus B. Okay. Now from this triangle, let me write. Go here. Observe a triangle OAB. Okay. And then apply law of cosine. Oh, by the way, I think I've said this in the last semester. Anybody know what is cosine means? Cosine. You have sine, cosine, tangent, but what does it really mean? It is aside from the definitions from the triangle. It's just co means complementary, so it's complementary of sine. So you will see your graph of sine will be complementary with cosine. So sine and cosine is actually the basis is the sine, and you have the cosine to complement the sine. And sine means Observe. Like when you have the archer, the bow, the arc. Yeah, sine means arc. Yeah. So you apply law of cosine and apply for AB squared. Okay. AB squared and then OA plus OB minus 2 and then cosine. Okay. So why we are writing this? Because the definition or the terms we are using is the theta in which in front of AB, right? So if you remember the law of cosine, so AB squared is equal this squared plus OB squared minus 2 of this side magnitude and then cosine theta. Okay. So we apply the law of cosine. And let's define the OA is factor A, right? OB is factor B, okay? And factor AB is factor A minus B. So we can write this becomes A minus B squared. And this is the formula. And then cosine theta. Now for additional notes, okay, so let me write this as equation 1. For additional notes, let's write the A minus B squared equal. Let me separate the square, become A minus B dot A minus B. And let's make some calculation here. And then plus B dot B. And from here, we can say this is the magnetic value of A squared minus 2 A dot B and plus the magnitude of B squared. Now we are having the second equation. So this is the A minus B squared. Now we are putting this second equations into first equation. Okay. So exchange all A minus B squared with A squared minus 2 A dot A dot B plus B magnitude B squared, and then A squared plus B squared minus 2 AB cosine theta. Now we have, or we can cancel now the A squared, okay, and then B squared. Okay. Now the equations become this negative 2. We can also cancel, right? So that's why this formula becomes A dot B equal the magnitude of A, magnitude of B, and then cosine. Okay, so it's from the law of cosine. So A dot B equal A, B, and then cosine theta. So from these relations, if we want to find how these factors relate each other, we can find through its relations through the angle that both factors make. Okay? So when we say we have a family of these two factors, we can evaluate the angle between, and we can visualize how the vectors will be in the graphs. Okay. So you can write this as this also, and find or observe the angle. And the requirement should be A and B should be non-zero. Yes, non-zero factors. If it's zero, then we cannot apply this relation. Okay, still related to the angle. Oh, by the way, any questions before? Do you want to look at this for last time? Okay. So basically, you are using the triangle, using the law of cosine, and then try to make the law of cosine out of the theta. Okay. So from the picture, let me go back to the picture here. So the angle is here. So this is your first sentence. AB squared equal this OA squared plus OB squared minus 2 OA OB cosine theta. If there's angle here, alpha, so OB squared is equal this squared plus this squared minus 2 this cosine alpha. Okay, I hope you still remember the law of cosine. Okay, another thing, still in the angle, uh, it's about the perpendicular or orthogonal. So perpendicular is, let me just draw. Okay. Okay. Let me make. Okay, I think that's clear. So if this is two factors, if you have the theta is pi over 2, so if the theta equal pi over 2, let's say this is A, this is B, then two non-zero vectors A and B, all orthogonal or perpendicular. So whenever you find terms perpendicular or orthogonal, meaning the angle is pi over 2, which means in our calculations, this becomes 0. So whenever you dot the A and B, two factors, and it becomes 0, it becomes the requirement for perpendicular. So two factors are orthogonal if A dot B is 0. two vectors A, B are orthogonal if and only if. Okay, that's the perpendicular orthogonal. Okay. Still in the dot product, we also have other terms. Or maybe another notes for you, because this is not usually or not commonly used. This is, we already know, theta is pi over 2 becomes orthogonal each other, or A dot B is equal 0. The first one, the top one here, we call this is acute, right? It's smaller than pi over 2. And the dot product will be greater 0, right? And this will be, the last one is called the obtuse, the angle obtuse, and the dot product will be less than 0. Okay, that's just an additional notes. Okay, now let me move to the next section. The next sections will be about the direction angles and direction cosine. To explain these terms, we need to draw the three-dimension. And let's say we have I'm actually drawing the rectangle. Yeah, I hope it's become rectangle. And let the vector from origin, let's call this is the vector. Okay, let's say the vector A. Now, what direction angles means? is in this three-dimensional space or coordinates, if we define this vector A, then we can define angle from each axis. Okay. For example, we can define angle from X. Let's say the angle will be this. Okay. Let's say the angle from X is alpha. And then the angle from y-axis, is beta. Okay. And the angle from z, from here, is gamma. So from the picture, let me write the direction angle of a non-zero vector are alpha, beta, and gamma in the interval from 0 to pi. And this is that vector A makes with plus x axis, plus y, and plus z. Meaning that is this angle that we already drawn here. Okay. So that becomes the definition of direction angle. So if you have any vector, the positive axis from x, y, z, it can make an angle, and you can define them as alpha, beta, and gamma. And that's become the definition of direction angle. And direction cosine means, actually direction cosine is just cosine of that direction. The cosine of alpha, cosine of beta, cosine of gamma is become direction cosine. So it's kind of similar. And then if we are, let's say, mark this as A1 for the x, and A1 is actually the A dot the I, the standard basis vectors. So you will have A1, and then you will have A2 in Y, which is the A dot with the standard basis, the J and the K later. We can write the relations of all the alpha, beta, and gamma. So cos alpha becomes A dot I, the basis, divided by this. And because the basis is just one length unit, so you can write this in terms of A1 from the factor here, divided by A. The same thing for beta and gamma. So you will have A2 divided by A and gamma. And then by squaring all of the cosine here, the cos alpha, let's say squared, cos beta squared plus cos gamma squared. This all will result in 1. And we can also rewrite, so if A is equal A1, A2, and A3, we can exchange this A1 with cosine. So this will be A cosine alpha, A cosine beta, and A cosine gamma. So we can write A, and we factorize the magnitude. It will be cosine alpha, cosine beta, and cosine gamma. And therefore, we can write A which is confirmed it is 1, right? The unit vector, because of the unit vector. So the magnitude of this is, if you square it, it becomes 1, right? Okay. And now the alpha, beta, gamma becomes a new parameter that we can also track and use to define some vectors. So if we have a random vector, and then we know we can apply the angle, then we can find, or we can track how the vectors will be in 3-dimension space. Okay. So this is the, so alpha, beta, gamma, this is direction angle. And the cosine is the direction cosine. Basically, the same applications. But anyway, out of topics here, I just find an interesting fact that I know you are maybe learning English alphabets from elementary school, but I'm not sure how you write your English. Okay? If I take A, B, C, D, E, F, how do you write G? Is it this or this? The first one, right? Because this is much easier. But the interesting thing is most of people, when they are given an image of G, the second one, with certain variations, like maybe it's not really like this, maybe it's like this, or maybe like it's just you put a slight change into this G, and most people don't know about it. Maybe you too. So if you are like checking your keyboard laptop, how the G will be, most people will forget. And it's already been some university did the research of that, why it's happened. So it turns out that because we are not familiar when we write our G, because we usually write our G this way, right? But I think one of few people that still write G like this, even in my writing. So yeah, but most people this part. Yeah, just an interesting notes that I just find out recently when I looking up some university and they did like, oh, this research of G. Oh, interesting. Okay. Okay. Uh, that's the direction angles and direction cosines. Okay. Okay. We still have how many? Okay, we still have times, so we can still go. I think maybe up until the cross product, maybe the introduction of cross product. But before the cross product, let me go to the we call the projection. Okay, let's say we have PQR point, and then we have this is vector A, vector B. If we are seeing these two vectors of A and B, if you want to make a projection, we can make from this vector A to B or this vector B to A. But since I'm obviously trying to make this B to A, let's make that first. Okay. Uh, so this will be the projections. But in these projections, we have two things. Okay? We have two things. First, we can project the only the value. Okay, so only the scalar value. That's the first one. Or we can project the vectors itself. So let's say we have the component here. Let's say this is the component of how to write this is component and A and B. What does this mean? This means scalar projection of B to A. Don't get confused. Okay, so comp and then you have A and then B. But how we read this is component or scalar projections of B to A. So the B is the one we are projecting to A. So that's how we are reading these terms. Okay. And then this is actually the scalar projections is if we write the all terms of dot product. Okay. So this B cosine theta, if we also look at the triangle here, of course, this is the cosine, right? If theta is here, this will be the B cosine theta, right? And in terms of the scalar, then that is just, it is, right? So just B cosine theta, and this is become our component or scalar projection, okay? The second terms is factor projection. So It's similar to scalar, but it has a direction. So let's say this is a P, Q, R, same. So let's project this. Let's say it's A, this is B, same as before. So let's project the B to A and make okay, and this become vectors. So we call this how to write usually PROG, the projection B and A. So meaning this is a vector projection of B to A. The difference is this is a vector. We have directions now. So we can write this as the terms in the scalar projection, but we are calculating the unit vector, multiplying the unit vector. Or we can simplify this, become squared and then A. Okay. So basically similar, but this is having a direction, and so we need just to multiply with the unit vector. Okay. So this part is actually our scalar value, but for that scalar value to have a direction, we need to multiply with the unit vector. Okay. So that's why the formula becomes like this. So basically, this is the same b cosine theta, this part. Okay. And since this example showing you like the possibility of the projections, let me just giving you some example. This is A, this is B. The same projection from B to A. If we have this kind of vectors now we need to make some extension, and this is our projections. So this is our projections. Okay, I hope with many kind of vectors, any directions, you can get familiar to the projections, how to make some projections to those vectors. Okay. And all the exercise I will send to your Moodle, and you can check. Maybe not checking all, but maybe checking some part of the exercise. Okay, that's the projection. Any questions? Okay. And now we are moving to cross product, in which the later part of vectors. Okay. Let me move to the next slide. the cross product. So why we need to learn cross product? So before we are learning the vector, how to add, how to subtract, if there is any scalar, how to multiply. If you have both two vectors, how to multiply, you have the dot product, right? And you will be resulting the scalar, right? Now, if you have A, B, two non-zero factor, how to find a vector that orthogonal, or let me write perpendicular to both A and B. So this is the thing that why we need to solve, or why we need the method of the cross product. Okay? So we can multiply A dot B and we have the scalar product. Okay? But if we have two vectors, A, B, two non-zero factors, how do we find any vectors, like maybe factor C, and we can prove that the C is perpendicular to A and B, both of them. So that's why we need the cross product. So first, to find this kind of vector that's perpendicular, let's start from define our vectors. So given two non-zero factors, let's say A and then B. And let's say we make assumptions first. Okay, suppose C is C1, C2, C3. And C is perpendicular to A and B. So what's the requirement? So A dot C, or A dot C, and B is equal 0, and B dot C is also 0. So first, that's our definition and assumption. Now let's make some calculations and confirming all the conditions. So from here, we have the dot product. So we can expand this equations, become A1 and A2 and A3, C3 is 0. So let's say this is our equation 1. And then B dot C, so B1, C1 plus it's also 0. Let's say this is equations 2. Okay, now we can eliminate some of this, but let's eliminate just C3. Okay, let's eliminate C3. So let's eliminate C3. So we need to multiply the top equations with B3. So multiply with B3, and this bottom equation multiply with A3. Okay, and then we are subtracting both of this equation. So subtract minus. Okay. Now we have A1 B3 minus A3B1 and grouping with C1 after so we multiply B3, we multiply A3, and we subtract them. And then plus A2 B3 minus B2 or let me write A3 first, and then B2. And then C2. So this equal 0. So if we see this form, we can conclude C1 is this, and C2 is this, right? Just solving these both equations. So C1 is A2 B3 minus A3 B2. And C2 is A1 B3 minus A3 B1. Now we have these equations, and we can substitute these equations to both 1 and 2, C1 and C2. You can solve from equation 1 and 2 with substituted C1 and C2. You will get C3 equal A1 B2 minus A2 B1. Yeah, so you can substitute C1 to the first one, substitute C2 to the second one also. And then you are calculating C3 from those C1, C2. You get C3 is equal A1 B2 minus A2 B1. Now we have C1, C2, C3 is equal that's the resulting vector after we substitute eliminate. Okay, so this resulting vector, this is called the cross product of A and B, and we are usually write this as A cross B. And usually you are using your right hand rules, right, to find where's the direction. So if you have this vector here, you cross them, and the vector that orthogonal to both of them are this one, right? The one that goes up like your thumbs, right? Okay. And how you find the result is try the assumptions and then eliminate, and this is intuitively becomes actually the cross product, okay, based on what we are defined. Okay, the C is perpendicular to A and B. Okay, so maybe let me write one more to make some conclusions, and then what we can do next. So definition or theorem. So if A is A1, A2, A3. This is, I'm just repeating the what we have done. So you don't need to write this actually. So cross product of A and B is So the results is a vector product or the cross product. And in order to help you understand, the concept, okay, remember the concept of determinants, okay, determinants. Usually the determinants is explained with matrix. And matrix is I think one of the best way to visualize how the cross product works, okay, the matrix. If you have only 2 by 2 matrix like A, B, C, D, its determinant, this is the determinant form, is AD minus BC, right? This is order of 2. If you have 3 by 3, let's move to here. The determinants of 3 by 3. So let's say you have 3 columns and 3 rows. So A1, A2, A3. So determinant will be A1 and then B2, B3, and then minus A2, B1, B3, C1, C3, and then plus A3, A3, B2, B1, B2, C1, C2. Okay. Okay, and the same results will be applied if you are calculating the B and C instead of A. Okay, so and why this minus? If you remember how do we define in the matrix? This plus minus plus. Okay. And you can also define this as minus B1. And then you have A2, A3, C2, C3. And plus B2. And minus B3. Also, you can exchange to C if you want, but it's just confirming that that is the same determinant. Okay, if you remember that the matrix in mathematics. Okay, so what I want to show you here is by using this determinant, actually we can relate this to our cross product. Okay, because it's the best way to represent the cross product. Okay? To visualize. Okay, so through matrix we can visualize the cross product really well. Now, the idea to help you understand is if you have A cross B and you have 3 by 3 relations, then the first part you can write I, J, K. And this will be A1, A2, A3, B1, B2, B3. And you can exchange all A1, A2, A3 with I, J, K. So you will have A2, A3, B2, B3, and then multiply with I, that's standard basis vectors, and then minus A1, A3, B1, B3, J, and then plus has become K. So you can write the cross product in terms of determinants. So whenever you are do not have any clue how to write this kind of formula, you can write in terms of the matrix, okay, the matrix or the determinants, the directly determinants. And what you are going to do is mark your first row with I, J, K, and then you can evaluate each of I, J, K, and you have each one its determinant. Okay, so that's how you are able to compute the cross product. Okay. And let me uh, draw the visualizations. What this is about. So this is A, this is B. Let's say this is the theta, and this is the result of A cross B. So by doing this, let me write that vector A cross B is orthogonal to both A and B. So we can prove this actually. How to prove it? Just dot the cross product to A or B. So for example, we can A cross B dot A. We can compute first. We can compute and dot A. Let's just write A1 instead of I. So that means we directly compute the A cross B and A. We dot product them. So we can compute all the terms. And then we can see that this is, and all is gone, which means it's 0. So therefore, A cross B is orthogonal to A and B. Okay, any questions? Okay, this is just showing that the proof that the A cross B is orthogonal to A. You can actually try if you want the cross product and then dot with B. This is also 0. Okay, since I already draw this, so we have A, we have B, we have theta, and we have A cross B here. We need to define relations between factor A, factor B, and its cross product with the angle theta. Okay. Let me write the theorem first. Maybe we don't really have time to write all, but let me write the theorem. If theta is angle between A and B, so the theta is from 0 to pi, then the length of cross product A cross B is and then sine theta. Let me write this first and explain it. So first, to prove, we can start with the define the length of vector. And then cross product definition. So we start from the left, the A cross B, the magnitude of A cross B. So A cross B, the magnitude, you can add the squared, right? The squared of the result from the A cross B. So A cross B has the ijk, right? And then the magnitude is the component of I squared plus component of Y, component of J, component of K. And then after we are squaring that, we need to group and then simplify our equations and becomes the A B sine theta. But I think I will I will solve this for next week. Okay. And there are some applications. For example, in some mechanical parts, you will see that you need the cross product to visualize what is happened, especially in the physical phenomenon. And I think after the cross product, we still have 12.5 and 12.6 equation of line and plane, and also the quadratic surfaces. But I will skip that. Not skip. Next week. Okay, next week. Next week, 12.5, 12.6. Maybe if we have time, we can have simple exercise, and then we can go to reviewing chapter 10 and 11. Okay. So next Tuesday, we still continue the cross product and maybe 12.5. Maybe if we have much time, we can finish until 12.6. So you still have a spare time for reviewing our chapter 10 and 11. Okay. Okay. I think I will stop here. Any questions? So we will have the midterm on 29. And maybe this Friday, I will send you maybe some exercise for last year midterm. Okay? But I think it will be different from you because last year I think 3 chapter. Yeah. Okay. Any questions? If not, then I will stop until here.